Today we will start a new topic and that is an introduction to analog filtering, more specifically analog active filters. Before we get into the details, I would like to motivate the topic, and we kind of brushed upon this in the very introductory class. Remember that today all processing is largely done digitally, and therefore you have an A to D converter that goes and drives a DSP, which then stores, processes, does all sorts of fun stuff. An A to D converter, remember, is a combination of sampling and quantization, and it is not appropriate to take the output of your sensor. I mean, could be the microphone, could be an antenna, whatever, right? And then even though the desired signal has a small bandwidth, right? As per Nyquist, let's recall that all that we need to do is basically say Fs must be greater than or equal to twice the signal bandwidth for us to be able to perfectly recover the signal from its samples, right? But that does not mean that you simply take your sensor. For example, let's say you have voice, right? And we know that voice is for all practical purposes limited to 20 kilohertz. So in principle, right, it should be enough to simply, if you just believe Nyquist and then basically said, okay, well, here is my mic, and then I have some amplifier inside the mic which gives me an electrical signal, and then I directly connect this to the input of my A to D converter. What is the problem with this approach? I mean, the signal bandwidth is 20 kilohertz. Let's say Fs is 60 kilohertz for argument's sake. So as per Nyquist, this is good enough, right? So are we doing okay, or is there a problem? Yeah, remember that while it is true that the desired signal has a bandwidth of 20 kilohertz, or B in this case, right? Okay, oftentimes the sensor output is not only corrupted by it's got not only the desired signal, but oftentimes is corrupted by what you call noise. In this simplistic case, I am just assuming that there is some broadband noise. The noise does not know that you want to satisfy Nyquist. It does not know the sampling rate. It is just noise. Okay, and what do you call its frequency components can be anywhere, right? Now, if there is nothing you can do about the components of noise that lie within the signal band plus minus B, right? Because it's impossible to distinguish whether a component of the noise, if that corresponds to the signal, or if it is noise, if it is inside the signal band, correct? However, noise signals that are outside the signal band are easy to distinguish, right? And here is a visual example. So let's say you are digitizing voice, and here is an example waveform that you expect to see, right? But suddenly, you start seeing stuff like this, right? There is a whole lot of very high frequency junk riding on top of your desired signal, correct? So if you simply sampled the noisy waveform at the Nyquist rate, what will happen Basically, you can see that the samples of the black waveform and the red waveform are simply not the same, right? Okay, and how can you do better? Again, it's a common sense thing. What will you do? If you look at the red waveform, you know that can't be the true waveform of voice, because no one can speak with, no one's voice output will have such rapid variations, right? So what do you do? What does your common sense tell you? Well, before sampling, you must smooth that the red waveform, right? And smoothing a waveform is basically the technical term for that is filtering, correct? Okay. In the frequency domain, it simply means that high frequency noise, right, can potentially alias into the signal band after sampling if you don't do anything. Correct? So, whenever you have, so for example, let us say you have a sampling rate which is Fs, right? If you had a tone, if the noise waveform had some component at Fs, how would that appear after sampling? A tone at Fs after sampling at Fs would appear like DC, and therefore if you are simply looking at the samples, you would get confused and think that the input signal consists of some DC, right? So, in a similar fashion, what comment can you make about what all signals can alias into the signal band? What all noise components can alias into the signal band? In other words, which all input frequency components after sampling will lead you to mistake that the input signal lies within a bandwidth plus minus B. So, you have, that's correct. So, basically these are all, so this is Fs minus B and this is Fs plus B. So, all frequencies of the form MFS plus minus in the range of M times Fs plus minus B, where M is an integer, can potentially alias into the signal band after sampling if you didn't know, if you didn't do anything else. Correct? So, if you want to prevent this from happening, what would you do? What did our common sense tell us with respect to the red waveform that you see here? You have to smooth the waveform. In other words, you need to put a filter between the sensor and before the A to D converter, right? And in this particular example, what kind of a filter, basically all that it means is that it selects something and removes something else. What frequencies does it select? It selects low frequencies and eliminates high frequencies. So, this is an example of a low pass filter. So, the symbol for the low pass filter is basically, you know, there is you knock off the mid and high frequency components, and that is the symbol for a low pass filter, right. So, and what is the job of the low pass filter? How will you specify the low pass filter? Pardon? And what else? I mean, what should be the gain? I mean, basically you want to specify the frequency response of the low pass filter. How will you specify the frequency response of the low pass filter? Let us say you go to a filter designer, right, and say, you know, give me a filter which satisfies these specifications. What exactly would you tell him? So, what is the pass band? 0 to B, you want the filter gain to be 1 in the region 0 to B, correct? Alright, what next? Pardon? Right, so basically it's not enough to say, one suggestion that I got was to say, oh, the gain must be 1 between minus B and B, and after that it must cut off like this, for instance, right. It sounds like sounds like a plan, right, but there is obviously something wrong with this kind of specification. What does it mean? I mean, remember that we live in a real world where nothing has a derivative which goes abruptly to infinity, right. So, you can see there is a discontinuity in the magnitude specification, in the magnitude response, right, and therefore, it means that it is not possible to realize in practice, okay. So, you have to be a little more reasonable. I mean, if you are adamant and say, well, I want the gain to be abruptly 0 beyond a certain frequency, right, then the filter designer is going to tell you to go and take a hike. simply because that's not physically possible, right? Now you say, okay, well, let me be a little more reasonable, and what should I do? What would you then do? I mean, do you really care about the response between B and Fs minus B? Okay, so in other words, how will you specify the response? We come back to the question. So it's clear that you guys just can't say I want everything beyond a certain frequency to get cut off. Correct? All right. So how would you specify the response? I mean, what do you really care about? You care about the fact that the gain in the bandwidth up to bandwidth B is 1. What else do you care about? In the alias bands, you want the gain to be not low, you ideally want it to be 0, right? So the way you specify the filter response is, well, here you say it is, you want it to be 0. Okay, all right, and in this kind of region here, you're not very particular, right? Okay, you probably, as long as the attenuation in the alias band is sufficiently large, you probably don't care about whether it does this or whether it does this, you probably don't care about it, all right? Okay, so that's how you specify the response of the filter in practice. Okay, so this is what is called a brick wall specification, right? So let me reiterate that. Okay, so the question is, okay, well, then the filter designer comes back and tells you, oh, sorry, while it is just like how it's not possible for me to give you a filter whose gain abruptly changes from 1 to 0 at a certain cutoff frequency, it is also not possible for me to give you a frequency response that is absolutely constant in the range 0 to B. Does it make sense? Right? And therefore, then you back off and then say, oh, well, right, this is what I will call my passband edge. This is omega, right? We can always say the DC gain has to be 1, right? If it's not 1, you can always, put an amplifier so that the gain is 1. And how would you specify the passband? How would you specify the filter's passband, right? So the gain of the filter or the magnitude response of the filter, which I call h of j omega, right, must be can you mathematically tell me what we should put down there? Mod h of j omega must be greater than say basically must be greater than equal to A1 less than equal to 1 for omega less than omega 1. And what else what else could you say? That's one specification. What else would you say? Yes, Karthi, what do you think? Is that good enough or what? Is that a good enough passband specification and we can move to the stop band, or you want to add something else?
I guess you also need to specify within what the frequency falls down to the stop band.
Yeah, but isn't that automatically specified if you basically say, so you have basically the edge of the passband. What else do we need to specify the for? Yeah, you're right. So what?
The start of the stop band.
Yeah, can you basically, there must be a mathematical way of saying that, right? What do you think you can say? Very good. So, basically we say, okay, well, there is some omega 2 which I call, what would I call, if I call that the pass band edge, what would I call this? Stop band edge. All right, and this is A2, and basically you say, oh well, I want mod of j h of j omega to be less than or equal to A2 for omega greater than omega 2. All right, and as you can probably imagine, there is no unique way of achieving this. There are any number of ways of doing this. For example, you could have a response that, say, does something like this. Oops, this doesn't meet the spec. Something that does this, right? You could have somebody else come up with something else which does something that does that, right? As you can imagine, there are any number of ways of achieving this magnitude response. All right. So, the question, so in this course, I'm so the way of approximating these this magnitude response, right, is a huge topic in itself, and there are whole courses devoted to approximation theory. And what are the constraints under which we operate? I mean, you just can't draw a curve like that and say, yeah, well, this is my response. I mean, finally, it has to be realized in practice, right? And it has to be realized using elements that we know, namely resistors, inductors, and capacitors, and perhaps active elements to be able to replace some of the inductors, because the inductors can become very bulky, right? So, what we are dealing with is h of j omega, therefore, is the frequency response corresponds to the frequency response of a transfer function h of s, right? And this h of s, because it consists of only resistors, capacitors, and inductors, must be a ratio of polynomials in. It's a ratio of polynomials in S because we're using lumped circuits. It's a ratio of polynomials in. Correct? And because it's a ratio of polynomials in S, there is obviously a constraint on what form that h of j omega can take. It can't be an arbitrary function. It has to be a ratio of polynomials in S, whose magnitude response must satisfy these specifications, right? So, the name of the game, therefore, is to say, determine n of s by d of s, so that, right, mod h of j omega satisfies magnitude response specification. All right. And to make life simple, right, we basically say, oh well, let's start with simple things first. So, h of s is n of s by d of s. We will assume, and there is no particular reason to do this except simplicity, assume n of s equals 1. All right, and So, therefore, it is only d of s is a polynomial, and we, I mean, finally, when you say you have a polynomial, how do you specify it? You specify it by its order, right? You assume that is an nth order polynomial. All right, and such filters. So, obviously, you can see that this transfer function has got no zeros, it has got only poles. So, these what do you think you would call these such filters? These are all what are called all pole filters. And the reason why they are called all pole filters is obvious.